approximate about 270,000 of the over 900,000 bridges in North America. They constitute around 1% of the new bridge construction. And so when you think of timber in terms of using timber in existing timber bridges, maintenance is what triggers the purchase of a lot of timber elements in existing bridges that still are in service today, and thousands of them still in service in Atlantic Canada. So maintenance is a hot topic because maintenance extends life and continues to provide service for the community. We already know from talking last session on design that timber bridges, if properly designed, can be designed for 75 to 100-year lives. And many bridges have been in service a lot longer than that, some 200 years or more. And we looked at examples of those last week. And with regard to maintenance, we often think of the cost of timber bridge maintenance as being too high. If there are bridge owners, lots of times we hear, oh, timber bridges are so hard to maintain and they're costly. I just look forward to the day I can replace it and build a nice concrete or steel bridge. And so I thought I'd address that comment by just showing the state of the art and the published domain on the topic, where investigators in the Swiss Institute and other institutes around the world looked at what does it cost to maintain a bridge, whether it be timber, steel, or concrete. And they compared the annual maintenance cost for timber to steel and concrete. And quite frankly, wood fared very well, as you can see here, in terms of the range of maintenance cost in terms of a percentage. And one of the reasons that wood, I think, gets the bad rap for this maintenance cost perception is that when we think of wood, lots of times we think of decaying wood. We think of our decaying decks out back of our homes and fences where the fence posts decay, or telephone or utility poles where they decay at the ground line. And we think of decaying wood and we think to ourselves, oh, I couldn't build a timber bridge out of wood because it would decay. Well, that thought process has its genesis in some logical assessments. 82% of all timber bridge degradation is due to fungal attack and fungal decay. But that decay can be prevented through careful design, chemical preservatives, and other proper ongoing maintenance is what we're going to talk about today. So just because it's timber doesn't mean it can't last a long while. If you'll remember last time, we talked about what are the conditions for decay. If decay, organic decay, fungal attack is 82% of all timber bridge degradation for our timber bridges in service today in North America, 270,000, what are the things we can think about doing as we maintain them to extend life? Well, the conditions for 82% of the degradation process, the conditions for decay, are occurring when temperatures are between 5 and 35 C, moisture over 22% by weight, and oxygen over 21%. And of course, we have the wood source, the food source for decay. And look, it's a good thing that wood decays. People are going to say, what? What's he talking about? Well, it's a good thing because you know what? If wood didn't decay, there wouldn't be the cycle of life. And you couldn't walk through the woods today, the forest, because every tree that ever fell over would still be there. So the process of decay is a natural occurrence, and it's the cycle of life, and it's a good thing. And the decay-causing fungi, the spores that they produce, the seeds, they're inherent in most living trees now. And when the tree falls over or dies, they're the cleanup crew. We just don't want the cleanup crew at our bridges. So what is it that we can do? Well, we can't stop the temperature. We're not going to be able to have our bridges be kind of all heated. They're outdoors. And oxygen, you can't do much about that because we need 21% to breathe and live. And so we're not going to take the bridges away from oxygen. But we can deal with moisture because we know some things. We know that an open deck bridge in North America has an average moisture content of 16%. And a closed deck bridge has an average moisture content of 14%. Well, if this is the case, both those percentages are under 22. Why is fungal decay 82% of bridge degradation? And the simple answer is vertical fasteners that start from the top. If there's one thing from today's talk that I hope you gather and understand and use in your own lives, don't drive vertical fasteners from the top. When you do, it lets the moisture into the core, to the bright wood, we call it, and trouble starts. So as I said, this temperature range, 5 to 35, is a good ideal temperature. Well, this morning I was over at the Milky's Inlet Bridge, number 1. We're restoring this covered bridge, 100 years old, 215-foot spans. And I want to tell you that there was no decay growing in that bridge today because it was cold, well below zero. And I'll tell you, it's not growing. But when the temperature comes up, why, it grows. That's why wood that's in cold climates will often not decay nearly as quickly. This moisture content is the driver, and what can we do to change how moisture content impacts our timber bridges? Well, this is what this talk is going to center around today. We talked about oxygen here, for example. As I said before, when we see timber below the water, I showed you last week how logs, southern yellow pine logs, were submerged and waterlogged, no oxygen, and they'd been down there for a long while, and guys were getting in with the alligators to get them up to saw flooring with. This is an interesting, I just threw it in today because a friend of mine who's got me helping him restore a 100-year-old wooden boat that's docked down in Beaufort Sound in North Carolina. He sent this to me. He lives in the Bahamas and he knows I'm interested in wood. And he said, Dan, look at this. They just discovered all these mummified caskets, I guess you'd say, these entombment, and they're all timber. They were buried in the sand, out from oxygen, dry, and they're still there today. And inside the skeletons are mummified, of course, 3,000 years old, made of wood. Well, how is it that they could last 3,000 years? Made of wood, not treated, not diffused, or not fumigated. When the wood in our bridges, our timber bridges, can't last even 100 years, according to some. Well, I'll tell you the reason, and that these guys didn't have any oxygen and they were dry. And so if we can do the dry part with our timber bridges, we're going to get where we're going, and that's important. Food source itself, of course, is always going to be there. The timber bridge is timber. What else is new? Chemical preservatives can make the wood an undesirable food source. In other words, they make it inedible. When we treat a timber bridge with pentachlorophenol or copper naphthenate or CCA or AZQ or one of these preservatives, what we're really doing is making the wood inedible. And most preservatives, in fact, all preservatives, can't treat all of the piece. There's always some residual portion of the wood that's bright, that's not treated. And when we put a bridge together with wood treated and we drill holes and drive spikes into that bright wood, we expose it to decay. So that little preface leads us to this top 10 methods of improving timber bridge maintenance. And I'd like you to keep these in note. And if you want to request a copy of this, you can. And you'll see these top 10 methods of improving timber bridge maintenance that I've developed over my career. And you'll notice the starting one is change the vertical fastening. Don't drive vertical fasteners from the top ambient face and allow water to follow the trace down and get at the bright. Stop the use of meltoid barriers. So many of us, you'll see bridges where they have meltoid barriers on the tops of piles underneath the caps. Then they'll drive drift pins through them, and this meltoid barrier, bent metal, felt paper, asphalt shingles, whatever. When you drive the vertical through it, the water runs through it, it keeps it from evaporating and leads to decay. There's only one place that meltoid barriers serve a purpose, and that's between concrete and timber to keep the moisture out of the timber, but not between timber layers. Ensure positive drainage. People say, well, timber bridges don't need drainage because a lot of them are open deck. That's not true. All timber bridges need drainage. Provide for proper moisture content change. So many times I see people putting steel side plates on green large dimension timber, and they're not allowing for the timber to shrink, and the fastener will hang up on the timber and lead to cracking and cleaving. Stop the use of bending. You see it all over the place. People use compression bands around the tops of piles where the piles are beginning to braid because the vertical drift pin they used, which they shouldn't have, has led to decay in the bright, and the top of the pile is decayed. And what's going on is it's braiding or feathering apart, and people go in and bend it. Stop the use of near-end drift pinning. That's a place where you drive a drift pin close to the near end and it leads to cracking. Provide proper clearance for the breathing of elements. Let them breathe. Don't put bent metal up tight against them and let it sweat every day with temperature change and lead to moisture content and decay. Stop the use of heavy percent solids coatings. Don't paint large dimension timber. I'm telling you now, if you've got a dimension, minimum dimension greater than 2 inches, 50 millimeters, don't paint it with heavy solids paint. Stain it. Something less than 29% solids. Even the best paint is going to be brittle. It'll kind of crack over time, and it doesn't look good because the big dimension timber shrinks and expands, and use a stain. Number 10, use proper sized elements. This is particularly true of most old timber bridges in Canada, for example, where the caps have been designed to carry girders and they carry them for directly over the pile. And when they increase capacity of the superstructure, they add girders, and that puts girders between pile tops in the cap span, and we see horizontal shear cracking. Now let's look at each of these. Number 1, eliminate vertical fasteners. Look at this. In Ontario, here's a cap and a pile, and what's going on? Here's a vertical drift pin in here, got in behind the treated wood and led to decay by moisture in here. It completely decays, and now they're putting pieces of 2x10 from Home Depot in there trying to keep the cap straight. Look at this one, another one, a vertical drift pin, taking a pile completely out. Well, people say, well, Dan, what would you do different? I wouldn't drive a drift pin. I'd have an angle bracket where all the connectors are horizontal and stay away from vertical drift pins into bright. How many bridges do we have to see across Canada that look like this before we start to say as engineers, maybe we should be doing it differently? And why do we do it this way? We do it this way because when we went to school and get taught about timber, we found some old book about how you join timber elements together. And in this old book, it showed you how you connect caps to piles and use drift pin. And you know, it isn't right. It wasn't right 100 years ago, and it's still not right today. And we need to be changing how we do things. Look at this bridge in Hamilton, Ontario. Perfectly great Douglas fir girders ruined by attaching the deck with vertical spikes here. Look, it had to be replaced. Look what it does to them. So don't do it. There are different ways to connect the decks to the tops of girders and girders to the tops of caps and caps to the top of pile. Don't do it. Well, you say, Dan, I can't go out and change all my fasteners in my existing bridges. There's not enough time or money to do it. And I'm saying, well, no, you can't change the past, but you can change the future. You can't live life looking in the rearview mirror because you'll trip over your own feet. But what you do when you go forward maintaining your timber bridges is maintain them right. So in this particular case, the guy on the right had a chance to get rid of that vertical, and he did. The guy on the left hasn't gone yet, but he's going to be. As soon as they get an opportunity, they switch him out and do it right. So you see here, here's a guy, he switched it out. He put the horizontal and eye bolt, but what did he do? He went down through the cap. So he got it half right. And these guys are horizontal. This is a switch out where we took all the verticals and switched them out to horizontal to help the bridge last a lot longer. Here's a girder where instead of fastening it to the cap with verticals, they have a horizontal here, angle iron, very simple, and an eye bolt up top here. It's got threaded adjustment. When the girder shrinks, they can keep it up by tightening the nut. A great way to keep it going. This is meltoid barrier here. Look at this. Meltoid between what? The deck and the cap. Sorry, the girder, and this is a corbel, in here between wood layers. A poor choice leading to decay. And what's going through it? Look at all these verticals going through it, leaving water up in here to nest. Under here, it can't evaporate, and it holds it over 22, and it decays. Look here again, meltoid barrier between the deck and what? The girder, leading to decay. Here again, beautiful girders. They decided they're going to put new precast concrete deck panels on top of them. It was going to last forever, and the engineer designed it. He designed countersinks here for the legs and the bolts, put in a meltoid barrier and legged them directly into the tops of the girders. Within 3 years, the edges of the concrete deck panels were getting beat off. They brought me in and said, what's going on? We looked at the girders, and 4 years out after installing, they had to replace all the girders. Why? Because of one simple mistake. verticals from the top. Ensure positive drainage. Look at this. No extension on this drain, letting the water roll over the elements below, keeps them saturated and leads to decay. But hey, don't let that water get on a galvanized steel pipe, boys. We don't want that. We'll let it roll on the wood, but we won't let it roll on the galvanized steel pipe. So see, it's about protecting wood and planning for it to last a long time and not letting this occur. This one here, as I explained on our first trip, they had a pothole situation developing on the asphalt above, and so they were hydroplaning, and so they sent the crew out to install the drains. And they had these cross bearers at 4 foot on center, and they said, go install a drain every 20 feet. So instead of starting at the 2 foot mark, what did they do? They started at the abutment back wall and put a drain over every location over the cross bearer. They put the water right on them without an extension. The extension cost $2.49. They didn't do it. So not long after they had the drains installed, the cross bearers started to lose compression perpendicular to grain because it was saturated and decaying. So they sent the crew out again to put 2 Kentwood pieces of treated wood. Because they couldn't get them in the same depth, they had to put them in a little shallow and put 1 shim. About a year later, these guys were shrinking and they had to send them out again to put a 2nd shim in. And then about a year later after that, they started to get decay again, and he started to lose. Over 3 different trips to the site, no one put an extension on this drain. You see, we don't understand timber. And when we don't understand it, it doesn't serve us well. Look at this, same thing. These bent metal fasteners and leading to decay. Allow for shrinkage. You can see here all of the ways we've allowed for shrinkage. You see the stitching plate for back wall planks. You can see this lift nut here in a cylinder on a cylinder. This is a rotating cylinder on a cylinder for the girder end that allows for skew, various skews, and these nuts allow for up and down mobility as the shrinkage might occur in these girders. The shrinkage here on this gauge beam underneath a deck-to-deck panel butt joint, where these are ovaled out to allow the deck panels to shrink and expand with moisture change. See the slotted route here, where the Z-clip attaches to the bottom of the deck. It's in a slot, so this deck panel can shrink back and forth here when this longitudinal orientation of the beam, which doesn't shrink in a significant amount, is not moving back and forth. This guy is, and allows that movement. Stop the use of banding. Oh, my soul, I can't tell you what happened with this band. $1,000 a piece for a galvanized band. $1 million of bands in this one bridge. And the first band they put up ended up here, and they closed the jaw with this adjustable nut and bolt scenario and couldn't hold it. Look at this guy. It didn't work the first time they put it on, and it isn't going to work the second time they put it on. If you got to put finish nails on a compression band, you know it's not going to be working effectively. You can see here, it started at the edge, it's now back here. So these situations where we use compression bands, as I go back and forth here, are evidence that what we're trying to do with compression bands, that's contain the pile, is not working. Why? It didn't work for Grampy, and it isn't working for his son. Why? Because when we put a drift pin in here, or vertical fastener, and it decays from the inside out, this compression band is not going to stop the wood from buckling in. It's designed to stop it from buckling out like a broom, a band on a broom, but it doesn't stop it from buckling out. Buckling in, rather. And when it buckles in, what happens to the compression band? It gets loose and slides down the pile. That's why we put finish nails on them. It doesn't work effectively. We'll talk about how to beat this wrap in a little bit. Stop near-end drift pinning. You can see here what happens with near-end drift pinning. You get them too close to the end and they split. And look here, split and split. Provide room to breathe. Don't put concrete up right around the ends of the girders, as you can see here, hold moisture and let the water stay in the seat area here and lead to additional decay at your reaction point. You can see here area poured in, scour protection in and around the bent, poured it up around the sills and up around the cross braces, holds moisture nice, holds air nice, and the first thing you know, it's decaying. Bent metal on the tops of guardrail posts, you can see here, sweats every day, tops of this pile here, or this column, they think they're holding the water off it, they think they're fixing it. They would be better off to slope cut it heavy copper naphthenate solution, 2% reactive agent or more, and then anchor seal it, a paraffin wax and water to keep the water out. Avoid high solids paint. How many times do you see curbs painted across Canada? They want to see them in the fog. That's the idea, but you can use a stain that stands out in the fog the same way paint does and not encapsulate a curb and let it hold moisture, put verticals into it to create moisture in the core, and then wonder why they decay so early. Avoid notching. Here's a bent, what we call a girder curtain, where we've notched the middle for a diaphragm beam and ended up having to try to hold the notch reentrant corner crack with another vertical up through it. And it just continues to lead to degradation of the bridge. In a sense, the blind leading the blind, and our timber bridge trying to do its best to last a long while, and everything we do to it seeking to shorten its life, as you can see here. This reentrant corner crack coming from this notch. How many times do we see people replace girders and bridges? In order to get them in, they have to notch them and put a packer under the end in order to get them in. And instead of slope cutting the notch, what do? They notch it square and leave it, and abrupt differential stiffness leads to tension per peeling forces, and away it goes. Here it is again. Use properly sized caps, pile caps. You can see here they've added girders to increase superstructure capacity. The girders were designed to be at the top of the piles. When they put them in the clear cap span, increased the shear, and led to shear cracking. So let's look a little bit more deeply at this business of timber bridge maintenance by looking at it from an inspection point of view. We've got to be able to find the bad actors if we're to fix them. We know that biotic agents like fungal decay lead to 82% of timber bridge degradation, insects, marine borers, or other ways. There's non-biotic agents, mechanical damage, truck strikes, for example, or metallic corrosion or chemical, UV. Fungal decay seems obvious when you go looking for it. You'll see a flower, a fruiting body that a fungal colony has put out and grown on the surface. That's an indication that somewhere in here things are not going well. And you can see the inspector putting a bore sound hole in here, and he's going to use a probe to see what's going on in behind here. There's another fungal fruiting body. Fruiting bodies have different looks. They take on different characteristics. They don't all look the same, as you can see here in these different photos. This shows you a picture of 3 different logs that were sapwood decay, and the engineer of record came by and looked at them and said they all got to go. And of course, we had a chance to walnut shell or garnet shell blast them and clean them up. And when you clean them up with a garnet shell blast, it takes a soft decay tissue away. And what does it reveal? It reveals that the decay follows a softer, less density woods. And you can see here how it's moving in and around that piece. So the idea of sound boring or drilling a hole into it and sticking a probe in it to find the cavities to know about decay really doesn't work, because how would you be clairvoyant enough to be able to drill a hole somewhere and figure out where the decay was? You see another example here. Another example here. And this shows you a pile where you can see how the decay has impacted it. Now, if I was going to drill a hole and stick a probe in it to find a cavity in this one, what would I do about all of these other losses of area? Or this one, or this one. So the concept that cavities form in nice round circular locations within a pile, for example, or a girder, just doesn't make sense. It's not the way it is, as you see in this piece. So you can see insects and marine borers also. This is white ants or termites, they call them here. And you can see marine borers here. You see this effect here of insects getting in after the wood's been softened up. And you see here more insect infestation. Look here, white ant trail. Insects have their way. And of course, marine borers have their way too. You can see this bent that's in a tidal zone where the tide comes in and out every day. And these men have 12-hour cycles to be able to get in, inspect, and then fix. Well, look at this. This is on the coast in Georgia, where they put these rubber skirts around the piles to keep the crustaceans off them, not really knowing that the crustaceans don't hurt them. It's the marine borers that do, and their idea is to keep the marine borers out. But what they do is create an eddy below this skirt, and the eddy and tides back and forth basically erodes this area around the pile, leaving this little narrow neck down path. Now, what would you do if you only had 12 hours a day to fix this? And secondly, you had 3 or 4 trains a day. What would you do to fix it? It'd be pretty tough. So we'll talk about that in just a minute. This non-biotic agents like, for example, ferric degradation. You can see this anti-splitter bolt. Grampy used one, a square head one. It didn't work. It split it. And then his son used this one here, another anti-splitter bolt, galvanized, and it still split it. And so these anti-splitter bolts generally tend to split. This is a Kentwood piece. You can see here it's got no boxed in heart. There's no pith core. It's called a Kentwood piece. You get this rust here that's going into this hanging chad, we call it, where they put angle iron through bolts through the deck and pinch the crossbarrel with it. Or this big fancy, what we call compression band here that was not galvanized and is bleeding all over the piece. More hanging chads. You see here, this is another typical vertical fasteners down through the deck panel, and underneath is a joist where they lose bearing here, sure as shooting, as this thing decays over time. The first thing you know, you're tramping here, and down through the board you go. This is chemical degradation. You can see this is hydrochloric acid in a digester in a pulp mill that burst, and the wood was impacted by acid. So decay, which is 82% of all wood degradation, impacts wood in different ways. You can see here it changes color, odor, weight, strength, all these areas. And when we're inspecting bridges, we watch for these characteristic changes. We perform external inspections and look at the piece with probing, pick test, hammer sound, moisture meters. We do sound boring, which I don't particularly agree with, drill holes and stick a probe in them. And we look for external things like fruiting bodies, sunken faces, staining, discoloration, and so on. Plant moss, like these fruiting bodies here, like this sunken face here, staining and discoloration, bulging faces, plant moss growth. And these external inspections are important for finding things. They're easier to find. The internal inspections, not so easy. The typical bore sounding, core sampling, which is good, stress wave timing. These are kind of some internal inspection methods. And this is what you call bore sounding on steroids, which I don't support anymore. I used to do this myself in the 80s, and I don't recommend it anymore because you create avenues for moisture and insects and everything else to get in there. And you keep on bore sounding it just because someone said to go bore sound it every other year. They keep on drilling holes. It had a cavity here. It's still got a cavity then. It's still got a cavity then. Why are they going toward the center? They're drilling holes, watching the cavity grow and move toward the center where the piece will become incapacitated. They stick a probe in this hole and see how big the cavity is. And here is what they've done is they've bore sounded it, stuck probes in it, calculated the cores, calculated the capacity rate on the piece. And the interesting thing was, the guy over here, this poor fellow over here, was the bad pile, and they didn't core him. And you can see him braiding because of the vertical drift pin here and loss of the center core. Look at this fellow here. What would you do here if you were bore sounding it to try and figure out its capacity? Would you drill here or here? That's why we use stress wave timing today and core sampling. You see Scott going in here, coring underneath this bolt here with this braces on, and typically these are culprits where the moisture gets in and you'll find cavity carrots underneath here. And he takes this core, and then we investigate it, develop specific gravity results, and use it to correlate the core together with the stress wave time values. You can see here these cores and these stress wave time values. Stephen, using the stress wave timer, shooting a compression wave through the piece. And then we'll have our cores and calibrate the stress wave timer here for different species in different situations that allow us to go around non-destructively, just have a stop and a start and calculate the time of flight. You can see the start and the stop, calculate the time of flight. And here's 7,233 microseconds going across here. Obviously, there's trouble in here where these vertical bolts are. And you can see here getting this time after he took the assay. So this method is a really great way to non-destructively test our pieces and find the bad actors and seek to know what the times are that would reveal whether or not there's a problem. And you can see there's a direct relationship between the stress wave time and the specific gravity. And the lower the specific gravity, the lower the strength if it's due to decay, that loss. In fact, as little as a 10% loss in specific gravity can lead to an upwards of 80% loss in compression perp, 75% loss in bending, and 65% loss in shear. You can see the loss is so great here that the log just dropped out under its own weight, because over here where the verticals were, the water got into the middle and there was trouble. You'll notice no verticals here. They don't even put the verticals in the middle because they know it kill them. So they put them in the end meter and it still killed it and it dropped out. Look at the fruiting bodies here and look at this time across this gap, all because of vertical fasteners. Vertical fasteners again, right in here. He couldn't see it. The log dropped out. And so he said, let's take a stress wave time. I'd like to see what the time is going across here when I can see inside and see the cavity. And the time was big. It was like 6,800, 6,900 microseconds. So what do we do to repair these things that we find, these bad actors? We got this pile posting requirements. I showed in a previous slide earlier about how this was a terrible design. We have a furniture joint, which is non-structural. We didn't have it sized down to match the stub. We had the fasteners going perp to the river flow, all bad characteristics in the design. And this happened, you can see here. So what would we do to properly post a pile? Well, AREMA and others post proper pile posting details. You can see it here. This is a proper pile posting detail showing rotation splines and an off-center shear drift pin and steel side plate. And let's look at what it looks like. So we stress wave timed this pile and found where we predicted the wood to heal up and go bright. You can see it here, still a carat of decay. And so Mark's cutting it down here and he's going to cut it down to bright. Well, we're going to clean it up some more. His first cut didn't clean it. So his second cut cleans it. As you can see here, we're all bright. And then what he does is put in an off-center shear drift pin in here, a pin that'll provide for shear. There's a hole here, a hole here. He's using an old log girder that they recovered a piece. It was good. It's dried out. They're going to put it over top of this pin, as you can see here. Copper naphthanated this, heavily anchor sealed it. Don't try to glue it, or epoxy is not going to work on end grain like this. Just get it over it. You can see here it forms a pin. It's got a lateral up here for lateral overturn. And now these are rotation splines. You can see where they're tapered. We glue into place a rotation spline to give the pile a rotation. It's got shear. And then you can see it glued in here. And this will then form a posted pile that's got 125% of its parent strength at the stub. Notice how the posted piece has been taper cut down to match the pile stub. It's rotation spline, shear pin, and then we side plate it or wrap it. And we can do this underwater. You can see Bill here, he's hanging on a swing. He's in 14 feet of water, and this is tidal, and he's basically using a hydraulic drill. I wouldn't go down there with a battery powered one. That probably wouldn't work too well. But down underwater he goes with a hydraulic auger bit, and he's posting a pile underwater. You can see his tools here. So you can post piles underwater with the snorkel gear and put a bent back in action. This shows you what happens when you steel sleeve it and put concrete on it, you kill it. And it's so typical. It's called potting a pile. And you don't get taught it in school, but you do find it in books. And I wish you'd throw those books away because they're no good. You don't pot a pile in concrete. It holds the moisture over 22%, and it shortens the life of a pile by 66% to wrap it and then put in the grout. So what we ended up happening here was this bridge had the piles replaced in 1942. And the piles that they drove in here beside it, they'd gone by wrapping them in concrete. And so I was looking at this bridge from the side of the river, and a farmer came by and he said, you know, I was just a kid when they cut those piles all off. They're down there at the riverbed. And I said, what do you mean? He said, well, the piles are all cut off down there underwater. And so I said, okay, well, I'll tell you what we'll do. We'll build the new bridge off those piles. And so I designed a solution to put a new bridge in place using the old pile stubs that had been cut off in 1942. And at that time, they were 100 years old. And we put posted pile pieces with reclaimed timber then put a bridge back on those old pile stubs to go another 100 years. And you can see them down here going underwater to post those piles, working away on the stubs. It's another posting detail showing you proper pile posting for an abutment bend. Now, we can wrap these piles with high strength fiber is another way to maintain timbers. The typical way of fixing a bad pile is to what we call put in a straddle bend. And you can see a pile on each side is driven in because you can't drive a pile in line with the bend. Firstly, you got to get it down through the top. Secondly, the cap's up there. Secondly, these guys displace. So they put a straddle bend in place. And if you got one sash high, they're typically about $28,000 for the railway to straddle bend a pile. Up top, they chain fall the tops together and put a subcap perp to the cap that goes lengthwise. Instead of that, what about this fix? Where this pile's bad at the ground line, come in and clean out the cavity, wrap it, inject it with 2 parts low cure epoxy, and fix it in situ. 28 grand, 3,000. 28 grand, 3,000. Guess what works best? So this shows you where all these wraps came from on this railway bridge in Richmond, BC. For the same reason, in Kootenay Landing East. Fix it in situ while the trains go, the 3 plums. So these piles, they get their strength. If you can see here, this axial test of a pile wrapped, they get their strength from the pile wrap. Now, people think, well, I guess we'll put the fiber up and down to get the strength axial. That isn't it. It's the hoop strength that gives you axial strength in a wrapped pile. And it puts them into slow ductile failures when they're properly wrapped, which is what we like. This is a totally decayed piece that was wrapped. So you can see the tops being wrapped. This is what you do instead of compression banding. Normally, they'd compression band the top. So why not wrap the top with a control top wrap, inject that cavity that's got formed at the top with a 2-part epoxy, put these yellow bungs here, that's diffusers that can diffuse in the wood, and cure this, solve this problem with a substructure, put a new super and deck on it, and instead of paying $3.8 million for a new bridge, you pay $1.2 million and you extend its life 100 years. You can see another one here, the same. Wrap instead of a compression band. Fix the base of this column and restore the bridge in situ. 765,000 versus 7.6 million new. The same goes here. Restore in situ. Now, people talk about concrete wrapping. This is what happens when you concrete wrap a dry pile. You think the pile's bad. You've got the wrong information. You go down, you put a zipper on it with a polyester wrap. You put the concrete inside it, inside a steel cage. You've got a cage you put inside it. And the water starts coming up inside the concrete pile because of capillary action. Water's drawn up in the pile. When the water's drawn up in the pile, what does the pile do? Expand. And when it expands, it puts huge hoop stress, 154,000 PSI on a 24-inch diameter dug fir top. That's a lot of stress, and it literally splits the concrete. You can't wrap a timber pile tightly. In this particular case, what caused the problem was not the pile, it was this. The cross bearers had shrunk, left a gap here all the way along this composite eye, and the engineer and inspector made the wrong call. So don't wrap your piles with concrete because you'll end up just drilling holes in them and seeing how fast they decay out as you see the sound bore. You wrap concrete around timber, what happens to it? Even the treated stuff decays. And you end up wrapping them with a band to try and hold them together. It just doesn't work, as we said earlier. Bands, you see, as we said earlier. I said last week I was going to show you how paper beats rock and scissors. Well, this is where I show you. You can see the seedling that grew in that granite boulder from the top down. You got some debris there. You got a fertile soil. The seed grew. And as the seed grew, it sent the tree one way and the roots the other. And as the roots grew in there, they expanded over time, and the power of cellulose to split rocks is obvious right in front of you. Now, who would think that I could possibly contain timber with a compression band if that is what timber does to rocks? So, in the old days, I grew up in a place down from Moncton, New Brunswick, close to the rocks. And there's a place called Grindstone Island. And they used to make grindstones for the New England seaboard, and they'd go along with their wood auger bits and drill holes in the rock. And where they drilled the holes in the rock, they would go around and put an oak dowel that they dried in the oven. And they dried this oak dowel down in the wood, and then go along and pour hot water on the top of the grain of the oak dowel, and the oak dowel would expand and split the rocks. And that's how they made many of their sandstone and grindstone rocks, was by splitting them with wood. So what happens there? Wood actually beats rock. And so therefore I've showed you now from last week what I said I would. That's how wood beats rock in scissors. I showed you this earlier, compression bands just not working, just not working, not working, not working. You know, they put these nail plates on the ends of pieces to try and hold them together and keep them from shrinkage cracking, and they just don't work. There's not enough capacity to make them work. $1,000 a pop, and it's got to have a set screw, and he installs it right on top of a cavity. You see, this is why wood timber bridges have high maintenance costs, is because the poor choice for maintenance strategies are made. We send people to a timber bridge who don't know how to perform proper maintenance, and asset managers get sick and tired of paying money into timber bridge repairs that don't last and don't make a difference, and they end up replacing the bridge anyway. So do it right, not wrong. It didn't work for Grampy. See where it is here at the bottom up against the cross brace? And it isn't working for his son because it's already come down from the top. The same here. It just doesn't work. Use the proper methods of wrapping and injecting and diffusing. Proper posting details. Look at this one. Take this. People said, well, I'm going to have to get rid of the whole band. I said, no, let's take an old piece of wood and fix this. And as I showed you earlier, we basically put it back in service and fixed it by posting the detail and putting a new cap in it on this piece, anchor seal, fixed it up, and restored that bend using all old materials. Extend the life of the bridge. It's still going now 10 years later, and it'll be there another 50 years from this. Properly wrapping, now properly posting. Now this is wrapping the post. You can do a wrap if you want as well to increase the capacity. Put the proper cross bracing on it and restore this in service. That's what it looks like there. So you can see these sorts of things as I just review them again. Concrete wraps don't work. They don't work. Don't do them. Now, Dutchman's patches can be used. You remember that bridge I showed you earlier where it was heavily susceptible to tidal zone, and it was 3 trains a day and 12-hour tide shifts. Well, what could you do? Well, the minute the tide's down, you could come in and do a Dutchman's patch. The core is usually good in timber that is impacted by erosion and wear from different sediments that are flowing by with the tides. So you can see here, Joe's taking the chainsaw. I couldn't do it. I'd cut it in half. But Joe's taking the chainsaw and he's squared it up. He's made a diamond here. This is made a certain way on purpose. And this diamond, he touches all the way up and down here. He's squaring it. And then he takes 2 halves. It's called a Dutchman's patch. You take the 1 half here, you pinch up your cap a bit, pull this half in, and then you put the other half on it and glue it to it. You can see here. And he basically used a Dutchman's patch, kept the same core. That way you don't have to frame bend or partial frame bend your bent. And he's going to glue this up and do it in the time it takes the tide come up. Notice where the water is now. It's come up around it. He's almost out of time and he's screwing it on. And here it is finished as the water starts to come in. That's called Dutchman's patch. You can see them here. Make them, all kinds of them. They're in 2 halves, and then you get them treated. So they're totally treated and they have a hole in them. So a port can you use to inject epoxy to fill little gaps that occur between the core and the outside. Now, what do we do with these pumping piles that we talked about last week? I showed you this picture where this guy's pumping. One of these piles is pumping. You don't do this. You don't shim them. That's just a pumping pile on steroids. You shim them, you're going to drive them deeper, and you don't notch them. And you don't maltoid barrier them. And so you see this poor timber bridge is still in service in spite of all of the mistakes that have been made to maintain it. You see, this isn't timber's fault. There's nothing fixing stupid. This is not timber's fault. Everything you can do wrong to screw over a timber bridge, you're doing, and wondering why the timber bridge cost you a lot more money, why his life is shortened, why it's too much to maintain him, and why somebody gets the approval to put a concrete one in. Because you've done this to your timber bridges. See, that's not timber's fault. And this one here, you put a soldier pile beside this guy where he's decayed out at the water line. And this one here, one's pumping and then the cap shears. And so what do? Put a precast concrete cap in
and the outside guys all crack because the load goes from 3.6 tons out here to 20 tons, and it can't handle it with the angle. And this is the Peace River, as I showed last week. Look at them all pumping. The way to do this is to cut that pile, put a bearing pad underneath here to help that sub underneath gather the load it needs and properly repair it, and put cross braces and a whale on each side and restore that bend. Look at the meltoid barrier here, and the drift pin is still here. There used to be shims in here because he's driven it this deep. And what happens now when the truck goes across it here? A truck goes across it, flex down and hits it. What happens when it flexes down? It puts extreme bending stress up here and shear in it. The first thing you know, the cap's gone. The pile's gone, the cap's gone. The first thing you know, an engineering group comes around and says, well, we got to turn that bridge down from 62.5 to 5 tons because it's in trouble. And then the first thing you know is the owners say, well, gee, this bridge has been costing me too much money. We'll just replace it in concrete. You see, that's the cycle we go through with our timber bridges when we ruin them. Look up top, bent metal fastened with nails to the end of that cap. Leave it alone. Don't put the bent metal there. If you want to do something to it, put paraffin wax to it or CN and shelf cut it. That's a boxed in heart. Put a shelf cut here and cause the drip edge to come in the middle, and do that before you treat it. And these are the ways we fix our timber bridges. Here it is again, look. Girder notches, we've talked about that. We've already talked about this. I just put it in here again because they're the ways we restore timber bridge. This is a boat to not a reentrant corner crack. He hasn't got there yet. He has. This guy took the whole girder out just for want of this. The simple little change would have prevented this. Simple little change. Simple little changes diffuse things. So what about fiber reinforced timber retrofits methods? What about the way of using high strength fiber to be able to bond to the bottom of girders and restore their capacity in situ so that you don't have to take them out? Well, these are popular ways today. We take these high strength fiber, 5 or 6 times the strength of steel and tension at a fifth the dead weight. We prepare them and we bond them to glulam beams. We bond them to the bottom sides in the tension zone. We can put them on RetroTen up here underneath this bridge in situ and increase its capacity. These 2 RetroTens right here are equal in capacity to all 4 girders. And we wrap them and fix this bridge in situ. And we can do it here nice because we just have to plane the bottom face, put our glue together, put the RetroTen up, and restore it in situ. As you can see here with Randy and James. They're putting the right torque on the legs to provide the right pressure to close the gap and make a thin glue line and cure it. And it can follow the undulations. This is where a snipe has been slope cut at the end. Shear panel. We can put shear panel on to improve shear capacity in caps where shear failure has occurred because of improper placement and pumpers. And the shear capacity can be enhanced up here in the girder as well. Increasing bending capacity. Installing these in situ while the trains run as you're improving the capacity of the bridge, extending life, increasing capacity, and improving the outcome for timber bridges. Shear panels for increasing shear strength where it's lost capacity due to vertical drift bending. The same goes in here because of vertical drift bend. Wrap them because of vertical drift bend. Restore in situ this bridge and put it back into service. This is a new bridge where we've enhanced the capacity of the girder with shear panel so that we can keep a size down 1 width class, and a truck crash-proof rail system installed too in this timber bridge. And this is a greenfield project, new. There's an old one restored again with shear panel, high-strength retro fiber, wrapping, keeping the bridge in service and increasing capacity, keeping the trains running. Look at these bands. Just, you can put lipstick on a pig, it's still a pig. And so these bands are doing nothing. They're useless. Sometimes the shipping department gets involved in doing it, and they're just not positive maintenance characteristics. Do the proper things to restore and improve the capacity of your bridges in situ. As you can see here with the shear panels, wraps. Take an old bridge out of service for 10 years. Rail bridge, 52 years old, hadn't been inspected for 10 years. turn around, inspect it, find the bad actors, restore it, put a new top on it, and put L110 heavy forestry loads across this bridge. Here's a bridge where Waja Bridge in BC, where over half the structural cross ties between the through girders were horizontal shear cracked. And we drilled holes from the top, injected the piece, and secured it. These are drilling holes for diffusers and injecting when we find cavities. Injection to basically infill the cavities to restore in situ. This is what it looks like when we restore the shear capacity of something. This is a piece that was cut in half after it had been injected under pressure to flow the two-part epoxy in the crack. Same strategy here. Don't drill a hole to put a bore sound in. Drill a hole and diffuse it. Fix it. Don't ruin it. Fix it. So there are different ways to prevent decay, as we talked about: preservatives, fumigants, and diffusers. Well, the preservatives are pretty common. I prefer oil-based preservatives like pentachlorophenol and copper naphthenate. I don't use creosote. It's a lumen treatment, much more. It's getting outlawed around the place. I don't use coal tar, but I do use pentachlorophenol and copper naphthenate. And most of my preservatives are post-machining. They're oil-borne, so they don't distort the wood by swelling like a water-based preservative would. In the railway industry, for example, they don't allow water-based treatments. They're all oil-based treatments. And copper naphthenate is available for a field preservative. I recommend more than 2% reactive agent in an oil base. As you can see, these various types here shown. Fumigants, what's the difference between a fumigant and preservative? A preservative makes the wood inedible. A fumigant kills the decay-causing fungal colony. The problem with a fumigant is that it tends to mobilize quickly through vapor pressure, but it also wears out quickly. And so as soon as it wears out and the toxicity level drops, then the decay-causing fungal colony starts up again and keeps on going. And so there are different types of fumigants. Mitzi fume, you can see here, trichlor, tripolon. There are many around that are available today, and a very popular way to fix utility poles, for example, because fumigants act pretty quickly, and you don't have to have moist wood to have it act, and it kills the fungal colony. The difference is you got to keep applying it in near term. You see here, this different types of processes here. Mitzi fume. Used to, in the old days, put arsenic in wood. And you have to watch it today when you see a skull and crossbones in a triangle when you're drilling into it, because it can be toxic. And a lot of old structures had arsenic. Diffusers are kind of a newer way forward that I've been using the last 10 years. They're basically a de-watered salt, a dehydrated salt. And the interesting thing about them is that they will lay dormant like mothballs in your wood until the moisture reaches 22%, at which time they start to brine through the wood, and they neutralize the acidic pH wave created by the fungal colony. So in other words, they tend to neutralize, not kill, and they only act when the wood has moisture contents where it would decay because of fungal attack. And so I like these. They tend to last longer. You put quality control checkpoints in your bridge, and you check them every once in a while in the higher moisture areas to see whether you need to replace them. And here's kind of what they look like. I like them because you can handle them with your hands. It's a salt, and it's a very interesting way forward. You can see the different places that we use them to restore and preserve wood in situ. It's what one looks like. You can see the radiation pattern here. It's about 150 millimeters it'll radiate. So generally a foot separation is the most you can have. And there's a certain volume of wood that so many of them will treat. Like this is a 3/4 by 3 inch, and it'll treat 2.9 of them will treat a cubic foot of wood, as you can see here. And this one's working because it's been saturated and it's drooling. I like to see that. So in conclusion, I just want to bring us to a close on the third round. I mean, I can't teach in 40 or 50 minutes a full maintenance course, but I hope that I have given you exposure today to the ideas of how to use high strength fiber to restore capacity, how to fix things in situ, how to do certain things like not notch things, slope cut your notches, how to not use verticals from the top, use horizontals instead of verticals, and not compression banding. Don't wrap them in concrete. You can Dutchman's patch them or post them properly. And a lot of these, maintenance details will be important to extending the life of your timber bridge, helping it to last longer and carry heavier loads and save the bridge owner money in doing it. And by properly maintaining a bridge and looking at timber bridges, as I have for 40 years, it gives you a powerful understanding of how to design them properly when you're designing a new bridge to go in timber. So with that, I'll open up to questions, and thank you for being on my last 3 webinars, and look forward to answering some questions now.
Okay, yeah, we got a few questions here, Dan. First one, you recommend to stop the use of metal compression banding. What are the differences with FRP wrap reinforcement of timber compression members, and does it perform better?
I understand you. So that's a good one. The idea with a compression band is that you're going to stop the pile from braiding outwards. What's caused that? Well, usually they're associated with vertical drift pins that have allowed decay to eat the middle out, and the vertical load that's coming on the pile tends to splay out the annulus, the treated annulus or the sound annulus. And the idea is that I'm going to put a band around it, pull it together, and keep it contained. But that does not prevent that annulus from buckling in. And when it does, it usually leads to the compression band sliding down the pile. And you have to hold them in place with set screws. So what's it really doing? Not much. What really needs to happen is that you need to contain the annulus with a wrap that contains it, and then inject a bulker, a 2-part slow cure epoxy, because you can't have a fast cure epoxy, it'll burn down the bridge. It's exothermic. So you have a slow cure epoxy that basically restores the center portion that's been decayed and allows the axial portion to pass down through that to the tip of the decayed carrot and into the pile and down into the ground. So they do work a lot better than compression banding. They're more effective and allow the extension of life.
Okay, awesome. Another one here is, what would you recommend for a small scale project like verandas instead of using vertical fasteners?
Listen, connect with me via email. I'll send them some details. There's bear clips, dowel clips. There's probably 3 or 4 or 5 different ways to attach your deck to your joist underneath the deck without going vertical. And here's the deal. If you're using a deck made from CCA treated wood or AZQ that's water based, and you're drilling holes through it and putting vertical deck screws down in it, wondering why it's only lasting 5 to 7 years in the Maritimes, that's why. So when you get deck stuff, buy PET, precision end trim. Don't cut the ends of your deck boards. When you cut the ends, you expose bright wood. It decays there just as if it wasn't treated. Secondly, don't vertically screw them down to your joist with deck screws. To attach them from underneath and don't come to the top. Use different clips. And when you do that, your deck's going to last a whole lot longer, 3 times longer to be exact.
Okay, awesome. Another one here. Is there a reference manual / document for all this information / techniques? Just a quick research online for timber piles repairs results in recent manuals with methods that this presentation recommends against.
Well, you know what? It's funny you should ask, because just now AREMA has finally passed after 5, 6, 7 years. I've been in the writing with many, many consultants across different walks of life for steel, concrete, and timber. It's the new handbook of conventional maintenance practices for railway bridges, which would apply to a highway bridge the same way. And in this manual, we have all kinds of different maintenance strategies, and it's going to be available on the marketplace here now in the next quarter. They'll be coming out to print with it. And to my knowledge, it's the only one of its kind. I have a McGraw-Hill text that Andy and I produced that has a whole chapter on renovation of timber structures. And I have a new one called the Wood Guide that it's a new textbook for teaching in Australia. And if Chris or someone would like to get a hold of me, I'd be more than happy to make available a PDF copy of those texts if they would like.
Excellent. And myself there, I just posted in the chat section a link to the PDF of the research that we just conducted with Dan Tingley's company as well for further resources.
Mm-hmm.
Another one here would be, what would you recommend for a deck connection of 2x6 deck planks on a timber pedesterna bridge?
I understand you. So he's talking about a 2x6 deck that would go across girders or something, or it could be longitudinal deck that's on crossbears. And how do we fasten them underneath is what he's talking about, so that they don't have the verticals coming from the top. My favorite way to fasten those deck systems is to use a little simple galvanized angle bracket. And that angle bracket will let you go horizontal into your joist and vertical up through the deck panel, and choose your screws so that they don't pass through the top. A vertical is okay in a deck plank as long as it doesn't pass through the top. So come from underneath with an angle bracket. That's my favorite way. If you can't get at the bottom because you're going over a gorge that's 50 stories high, then you've got some other details. There's called a dowel, a flat dowel biscuit joining method, a bear clip. They actually go down between the planks and they come in underneath the plank and fasten it to the joist. There, as I said before, there's about 4 or 5 really nifty ways to attach those planks. And look, I can't tell you how many times I see specifications today in Canada by engineers for bridge owners where they're specifying deck screws all the way down through from the top, deck screws. And it's just, it makes my heart sad all the time because it hurts our industry. Because the owners get these decks and they only last 5 or 6 or 7 years, and they're going out and the first thing they're saying is, I want to buy Trex wood composite decking or plastic decking or something else, and that hurts our industry. Because wood is a renewable product. It's carbon neutral or better, and we just need to be doing different things with wood. Understand what causes it to decay.
Excellent. And Yusuf has a couple questions here. And how does the life cycle cost of timber bridges compare with concrete and steel bridges? Any study on that?
Yes, there
And
is. And there's
there's information on that in this.
Get it out of yours. Yep.
That I just added in the chat section.
Right.
But I don't know if you want to add anything else
Yeah,
on
well,
top of that.
it's been proven by the Swiss Institute that the life cycle cost of, for example, here's some stats for you. The cost, the annual cost of a typical 20-meter clear span bridge, 2-lane highway, traditional highway loads, the annual maintenance cost for concrete is $980 some, steel just under $1,000, and timber's $486. You don't have to believe me, just go to the published domain. The cost of maintaining is less when it's properly designed. The life cycle analysis, if you think of my example of the Gardner Express Parkway with $1.8 billion spent on concrete bridge repairs that are 32 years old, it doesn't take much to figure out that the bridge I was at this morning, Milky's Inlet number 1, is a 100-year-old covered bridge, right? 100 years old. It doesn't take much to figure out that the life cycle analysis for timber is better than concrete and steel. Now, I know I tend to be a little biased, and people often say that I'm full of frazzes. But at the end of the day, timber has proven itself again and again to go the distance, last a great length of time, produce low cost maintenance for owners. All we need to do is think about timber in terms of what causes it decay when we're maintaining and designing it. And if engineers could just think that way when they're doing things, it would change the landscape of how we see timber bridges. What did people say? Well, Dan, timber bridges don't span as long. Well, that's crap. We have designed timber bridges 179-meter clear span. What steel and concrete bridges last going that long? I mean, we have timber bridges that are supporting L110 loads. We have timber buildings that are spanning 535-foot clear span. The 4th, 5th, and 6th largest clear span buildings in the world are timber. Concrete's dead weight is its own single biggest design. So, I mean, timber bridges go the distance. It's just about understanding timber when we design it. We used to have Douglas fir heli decks on our offshore platforms in UAE that lasted for a good 50 plus years. Recently replaced with steel decks for durability and safety purposes. So they got to be galvanized steel. Don't pit it with a screwdriver or a monkey wrench, because any place you pit it's going to bleed. and the timber isn't going to bleed. And the great thing about timber is that it gets in salt environments. If you keep the marine borers away from it, it goes longer. So I think it's just a lack of understanding as much as anything in good design detailing and maintenance strategies.
Excellent. Yeah, a lot of really good questions there, Dan.
Yeah, really good.
If you have any other questions that arise, I have added the email contacts for Dan and myself in the chats below there. So
Yeah, so I appreciate everybody taking time today to be with me. Maintenance is always one that's very popular, David, because, as I said before, we have lots of timber bridges still in service, and engineers are struggling to figure out how they maintain a level of service. I mean, governments, just because they decide they're going to build new ones with concrete and steel, it doesn't mean they're going to change every timber bridge they got out. There's not enough money printed in Canada to do that in the next 10 years. So we've got an average age of 82 years. That means we got to live with a lot of timber bridges across the country. And so engineers need to get with the program and understand how to maintain them and fix them and upgrade them and do it in a way that reduces cost, extends lives, and preserves level of service. The way forward with timber bridges, guys, is not to decide who goes first. I'll give this little example before you all leave me. I don't know how many people watch MASH. I used to watch MASH when I was in college at Fredericton. And in MASH, the helicopter comes in at the start of the show. And in the helicopter, there's two wounded soldiers, one on each side. And they run out underneath the helo blades to look at the soldiers that are wounded. And what they're doing when they go out there is they're doing triage. They're deciding who gets to see the priest and who gets to see a surgeon to get fixed up. If as engineers in every timber bridge across our country, all we become is triage to decide who gets prioritized for replacement and who gets a baler twine Band-Aid put on it, what good is that for the community? The simple answer isn't to constantly downplate all our timber bridges from 62.5 to 40 to 25 to 10. You get so bad you can't get anything over them. You can't even get a fridge delivered across the bridge anymore. That's no level of service. That's no way to know timber bridges and understand them. We need to understand our timber bridges and know what to do with them to maintain level of service and extend life. And with that, you've heard enough from me.
awesome. Yeah. And then there was just another one that just came through, and it was about is it possible to share the previous material, the previous webinars? And I just added a link, just our YouTube channel there where I'm going to put all the webinars. The previous two are up there along with a couple other ones that we did late last year. So if you want to check that out, that's what the YouTube link will bring you to our channel there.
Perfect.
So you can always have those for references.
Get to one of our courses. I'm teaching a maintenance course next week in Fort Myers, Florida. I got a one-day maintenance course, and we're going out to actually perform maintenance on a couple of timber bridges. And usually in non-COVID days, we have 16 different courses, level 1, 2, and 3 in each of maintenance, inspection, restoration, and design. And I challenge some people, get in these courses. They're continuing education units for the engineers that are listening. Get in there and understand timber, understand it and get to know about it so that you can speak in an educated way. Don't look up books that are 100 years old and figure out how you're going to fix timber bridges. There aren't many buggy whips built today, guys. Not many buggy whips, right? 100 years ago, people would have died from pancreatitis and diabetes. They don't today. We drive new cars, not Model T Fords. We do things differently. We design things differently. Let's think about timber bridges, their restoration and extension of life, with new ways of thinking that preserve life, that increase capacity, not decrease it, and reduce cost to owners. Thanks, guys.
Awesome, Dan. Thanks. And thanks everyone for attending, especially if you've followed us the whole way through the webinar series. With that, you'll be receiving a survey sometime next week, and your feedback's very important to us. So appreciate that if you could fill that out.
Thanks, everyone.
Thanks, everyone.